Scientists just discovered a Soviet Venus lander record that shows the ground changing in 17 minutes, but Venus sits at about 735 K under roughly 92 bar, so the surface should not update on camera at all. The contradiction looks small at first, but it grows teeth the moment the timestamps line up. And it matters now because 2026 kicks off a new Venus push, while a 50-year-old tape suddenly behaves like breaking news, which raises one question that won't let go. What exactly did the Soviets catch down there? Every photon in those panoramas bounces off rock at about 460 degrees, then reaches Earth carrying information that begins its journey before you exist. But that information now looks like it's been hiding a second story. According to standard surface chemistry, Venus rock weathers slowly. However, these logs show a fast jump that looks like the ground reacts in real time. That's like watching a frying pan change color while you stare, except the pan sits inside an atmosphere that crushes like diving to around 900 meters underwater. And if that change is real, the next question becomes brutal. Does Venus react to being touched? For 6 months, a 2026 archive team rebuilds Venera telemetry from noisy scans, mismatched clocks, and half-missing calibration notes, but the anomaly refuses to die. They blame thermal drift. However, the jump hits like a step, not a slow slide. They blame compression artifacts, but the change locks to the same patch of terrain while a separate reference stays steady. Then they look at the data one last time, and the jump lands on the exact moment the sampling arm touches Venus at T+plus 12340. And once touch becomes the trigger, the mystery stops being old data and starts being active surface, which opens the next loop. Why does contact flip the scene? The reveal snaps into focus inside the Venera 13 and Venera 14 surface sessions, but the shock comes from repetition. A reflectance channel climbs about 11%, the change stabilizes after roughly 17 minutes, and a temperature-controlled internal reference stays flat the entire time. Here's the crazy part. The effect appears at 2 sites separated by around 900 km, which makes one bad sensor collapse immediately. If 2 distant places respond the same way, the story stops being a glitch and becomes a mechanism, which forces the next question. What mechanism acts globally on Venus? But here's what breaks them. If Venus surface chemistry flips that fast, our equilibrium assumptions fail at Venus conditions. That means the equation of state tables we trust for supercritical CO2 at 735 K and 92 bar might not capture what the surface actually does when you disturb it. However, missions still design sampling tools as if the target patiently waits. If the kinetics run faster than the models, a lander doesn't sample ancient rock anymore. It samples a reaction happening right now. And if that's true, the next problem becomes terrifyingly practical. How many compositions we've measured on Venus are just the planet responding to the measurement? 3 consequences slam into mission planning immediately. First, future landers fail sooner in ways engineers misread, because Venus attacks materials chemically while the clock burns. Venera 13 lasts about 127 minutes, but Venus uses every minute. Second, textbook chapters on Venus resurfacing start to wobble, because fast surface change rewires how Venus hides its past. Third, NASA and partners face emergency-style design reviews in 2026, because a drill that creates chemistry ruins the meaning of sample. However, none of that matters if the whole thing is an artifact, which drags the story into the next fight. Is the signal real? Not everyone agrees, but the skeptic angle hits hard because it targets the weakest link. Old data. Dr. Kevin Rios at the Planetary Data Integrity Lab says, "You don't discover new Venus chemistry. You discover new ways to break old tapes." However, the team cross-checks housekeeping channels, and those channels stay quiet exactly when a heat glitch should scream. That doesn't prove the discovery, but it corners the skeptic argument into a smaller box, which raises the next question. If it's not heat drift, what else can produce a clean step change? But one signal remains unexplained because it doesn't look like drift, noise, or dust. At exactly T plus 14312, a pressure trace shows a sharp bump, then a slow decay, like a thump traveling through a fluid-heavy atmosphere, and the lander sits still while the planet answers back. Here's the crazy part. The team finds a second smaller bump near T plus 001, 1230, like an echo arriving late. If Venus thumps, the story stops being chemistry alone and starts hinting at motion, which opens the next loop. Does something push from below? The future part of the story depends on new eyes and ruthless timing. In 2026, observing teams stack night-side infrared windows around 1.02 mm and 1.10 mm because those wavelengths sneak heat signatures through Venus clouds, but cloud patterns can fake heat unless you subtract them perfectly. However, repeated flickers at the same coordinates beat cloud noise because clouds drift and fixed geology doesn't. If a hotspot pulses where the Soviet thump fits, the archives stop looking historical and start looking predictive. And if it doesn't pulse, the story grows darker. Either the old signal is the cleanest illusion ever recorded, or Venus changes in ways that dodge modern watching, which leads to the next chase. How do you catch a planet mid-change? Now the argument turns into a trap you can't escape without choosing a side. Question 1. If the ground brightens by 11% in 17 minutes right after contact, do you call that chemistry or instrument contamination? Question 2. If the pressure thump hits at T plus 14312, do you blame atmospheric waves or something? Pushing from below? Poll for the comments, volcano, chemistry, data artifact. Pick one and tell me what single measurement would change your mind, because the best theory deserves to be pinned. However, whichever option you pick has to explain both the brightening and the thump, which makes the next step unavoidable. Follow the physics of Venus itself. Venera doesn't float down like a balloon. It punches through clouds stacked around 50-70 kilometer altitude, and the environment turns hostile by the second. Near the surface, winds look slow, about 0.3 to 1.0 ms, but the density makes that slow shove like a heavyweight, and everything chemical feels amplified. On Earth, a reaction can fizzle quietly, but on Venus 92, bar forces gases to behave almost like liquids pressing into pores and cracks. That's like trying to weigh a melting ice cube. But the cube sits inside a pressure cooker at 92 bar and 460 degrees C, so your scale fights the room itself. And once you accept that scale, the next question sharpens. What surface layer can form fast enough to brighten rock in minutes? The team builds a rate model that asks what can form in under 20 minutes, and then stabilize like a completed reaction. But the output keeps pointing toward thin films and crusts. That sounds boring. However, thin films can hijack reflectance so completely that a spectrometer reads new composition, even when the underlying rock stays the same. Here's the crazy part. A thin film mechanism can repeat across 900 km if the atmosphere supplies the same reactive ingredients everywhere. But thin films don't explain the pressure thump, which forces the narrative to pick up a second suspect that can do both, a source of pulses. Volcanism doesn't need to throw lava like fireworks. It can vent gas in pulses, and on Venus that gas can rewrite surface coatings fast. A vent pulse can also deliver a pressure bump that hits a sensor like a knock on the hull, but the atmosphere crushes expansion so hard that it can look subtle instead of cinematic. However, a pulsing vent also refreshes local chemistry in predictable ways, which makes the 17-minute brightening look like a reaction to a fresh dose of gas. Once vents enter the story, the next loop becomes urgent. Can modern instruments spot today's vents where the Soviets once listened? That's where the 2026 campaign becomes a stake, not a footnote. Observers don't just want a pretty thermal map. They want repetition. 2 flickers separated by days, not 1 lucky pixel, because repetition turns maybe into measurable. However, Venus rotates slowly, about 243 Earth days, which makes timing windows unforgiving and forces global coordination to catch the same region at the right geometry. If a repeatable thermal flicker appears where the Soviet thump fits, the Soviet tape stops being a curiosity and starts being a timestamp. And if it doesn't appear, the story flips into its final, nastiest question. What did? The Soviets actually touch that modern sensors still can't corner? The Soviet lander's image fractured slabs and compacted material, not airy dunes which fits basalt-like terrain. But basalt under Venus conditions can grow coatings fast enough to fool instruments into reading fresh changes. So modern lander concepts shift toward high-temperature electronics rated near 500 degrees C, sampling cycles under 10 minutes, and protocols that measure immediately at 5 minutes, then again at 17 minutes, while logging pressure for a planned T+100.43/12 style pulse. That becomes a Venus speed run, not a camping trip. However, speed only helps if you know whether contact itself is the trigger. And that leaves the final loop hanging right in front of you. Is the reaction global, or is it a map of active zones? If Venus runs a global chemical skin, every lander lands on a surface that actively resets. But if Venus runs localized active zones, the Soviets accidentally hit two places near the same kind of activity, and that would be the luckiest and scariest coincidence in planetary exploration. Either way, the dead planet label dies first, because dead planets don't rewrite their own surfaces on human timescales. So tell me what you would build next. Do you design a fast drill, a touchless spectrometer, or a sacrificial sampler that expects Venus to react the moment metal meets ground? Subscribe for the 2026-2029 Venus results, because the next touchdown doesn't just land on rock, it lands on a process. Next week, the black hole that's eating itself.